Hello?
Yes, yes, Anish.
Sir, can you share the YouTube link, sir?
Yes, Surya Prabha, you can take the screen and you can share your first slide.
Okay, sir. Is my screen visible, sir? Hello, sir.
Yes, please.
Is my screen visible, sir?
Yeah. You share the slide. Actually, I'm seeing your screen. Actually, that share your presentation.
Yes, I am sharing it.
You are presenting to avoid infinite manner. This is what I'm seeing. Actually, you need to select this presentation slide. Yeah, your screen is visible, but it is infinite mirroring.
Now, can you see, sir?
Yes, I can see it. Make it in presentation mode. And 10 minutes for presentation and 5 minutes for discussion. The same is for the other person also. It is
Okay,
10
sir.
minutes for presentation and 5 minutes for discussion. Yeah, you can start. Start at 9. Okay, now.
Okay, sir. This is Prabha. I am here to explain the permittivity concept. Coming to the definition of permittivity, it is a fundamental property of a material that measures how much it allows electric field lines to passing through it. It also tells how well a material polarizes in presence of electrical field. As we all know, D is equal to epsilon into E. From this, we can write epsilon as D by E. From this, we can mathematically define epsilon as it is the ratio of electrical flux density D and electrical field E. Now, coming to the units, we know electrical flux density is defined as electrical charge per unit area. From this, we can write D as Q by A. We know the units of Q are coulomb and A are meter square. From this, we are having units of electrical flux density as coulomb per meter square. Coming to the electrical field, we know electrical field at a point is defined as force per unit charge. So mathematically, we can write here we can write E as force per charge, means F by Q. The units of F are Newton and units of charge are Coulomb. Now we can replace the units of force as joule per meter. This came from, like, we know work is defined as force into distance. From this we are having force equal to work per distance. So from this we can replace the units of force as joule per meter. And then we can replace the units of joule as volt into coulomb. From this, the both coulombs get cancelled and we are having the units of E as volt per meter. Now we are having the both units of D and E by substituting in the equation D equal to E epsilon. From this, we are having the units of epsilon as farad per meter. Here we can write coulomb per volt as farad because the units of coulomb per volt is capacitance. So the units of capacitance is farad. Coming to the types of permittivity, basically there are two types of permittivities. One is absolute permittivity and another one is relative permittivity. So the absolute permittivity is the actual permittivity of a material in the vacuum. So it is represented by a letter epsilon naught. It is having a constant value of which is equal to 8.85 into 10 per minus 12 farad per meter. And coming to the second type of permittivity, it is a relative permittivity, which is defined as ratio of permittivity of a material to the free space. So mathematically, we can write epsilon r as epsilon by epsilon naught, where epsilon is the permittivity of a material and epsilon naught is the permittivity in the free space. Here, The top part diagram shows molecules which are having positive and negative charges, which are randomly oriented, which means we can say that there is no external field applied. So in this, the both positive and negative charges cancels each other. So we can say that the material is electrically neutral. So we can say that the material is unpolarized. Coming to the second, like bottom diagram, uh, it is like when an external electrical field is applied, like we can show here by positive and negative signs on the plate, the molecule inside the material aligns themselves, as we can see in the figure. So we can observe that the positive end of the molecules turns towards the negative plate, and similarly the negative end turns towards the positive plate. As we all know, like positive attracts negative and negative attracts positive. So this alignment causes the polarization, which creates a tiny electrical dipole inside the material. So now we can discuss how polarization affects the permittivity. So basically, the total response of a material is having two parts. One is vacuum response, like which is denoted by epsilon naught into E, and another one is material's own polarization, which is given by P. So we can write the total electrical displacement or electrical flux density D as epsilon naught E plus P. Oh, and then coming to P, we all know that like linear dielectric material, in this we are having polarization which is directly proportional to the electrical field. So mathematically we can give the equation for P as epsilon naught xi E into E. Here chi E is the electrical susceptibility. So it is a constant term like which changes from material to material, like which measures how easily the material can get polarized. So now we can substitute this value into this equation. Like we are having the p value, right? This p value we can substitute into this equation. And then we can take epsilon naught and E as common, and we get final equation of D here. So we can see the equation of D as epsilon naught into 1 plus chi E into E. So we can compare this equation with epsilon into E. By comparing, we can observe that the epsilon value as epsilon naught into 1 plus chi. So from this, we can observe that, and coming to the next step, like if we move this epsilon naught to the left side, we are having epsilon by epsilon naught. So we know that it is called as a relative permittivity. So which is equal to 1 plus chi. So finally, we got the expression for relative permittivity, which is equal to 1 plus chi. So we can observe that as this susceptibility increases, we can see that the relative permittivity also increases. So from this, we can give an physical definition for a permittivity. So if a material is having high permittivity, we can say that the material can polarize easily. So that field inside becomes very weaker. And if a material is having low permittivity, we can say that the material cannot polarize much, so that it is having stronger electrical field than compared to the higher permittivity materials. Like now the real materials which are not purely real, so it is having both real and imaginary parts. So now we are having a term called complex permittivity, which means it is having both real term and also an imaginary term. So now we can express this epsilon as epsilon dash minus j epsilon double dash. Here we are having epsilon dash as a real part and epsilon double dash as an imaginary part. So coming to the real part, like epsilon dash represents the real part, like which is used or represents the energy storage in an electrical field. We can say that if a material is having higher epsilon dash value, we can say that the material can polarize easily, so that the capacitance also increases, and we can say that the electrical field inside reduces. Basically, if a material is having higher epsilon dash means it can store more amount of energy. Similarly, if a material is having lower epsilon dash means it is having less polarization compared to the higher value, and we can say that the capacitance decreases, and also electrical field inside will be more, and we can say that it is having very less, like it is capable to store less amount of energy. Now coming to the like imaginary part, it is denoted by a letter epsilon double dash, like, and it represents the energy loss in an electrical field. If a material is having higher epsilon double dash, we can say that the material is having more energy losses, so that the material becomes lossy. And if a material is having lower epsilon double dash means, we can say that energy losses are less, so it is used as a better insulator. So now we are having some practical examples here. All we know is like water is having higher epsilon dash value, like which is approximately equal to 80. So we can say that the water can strongly polarizes, and which significantly reduces the electrical field strength. And then, as I said in the before slide, if a material is having higher epsilon double dash, so there will be more number of losses, like more amount of energy will be lost. So we can use this in absorbers or microwave heatings. Similarly, if a material is having lower epsilon double dash means there will be less amount of losses. So we can use this in high frequency capacitors or antennas and in some other. Finally, like we defined imaginary and real part. So from those we can define another parameter called loss tangent. It is defined as the ratio of imaginary to the real part. Like this shows how a lossy material is. Coming to the mathematical equation, it is given as tan delta equal to epsilon double dash by epsilon dash, where I said before like epsilon double dash is the imaginary part and epsilon dash is a real part. Based on this, we can classify the materials into two types. One is good dielectric, another one is bad dielectric. So if it is having smaller loss tangent value, we can say that it is having very less losses. So we can say that the material is good dielectric. Like we can give an example like quartz glass is an example of a good dielectric, which is having very less value. So it is having very minimal number of losses. Coming to the bad dielectric, it means it is having larger loss tangent value. So there will be higher losses. So which is acts as a bad dielectric. Example we can say as a water. This is all about the concept of permittivity and complex permittivity. Thank you, sir.
Yeah, questions, please. Yeah, Prabha, I have one question. You have mentioned that the complex permittivity epsilon dash minus j into epsilon double dash. Is there any specific reason of keeping it as minus epsilon double dash? I mean, minus j into epsilon double dash? Can it be negative or positive or both? What that sign indicates?
I was not sure about it, sir.
Okay, thank you. So, yeah, thank you so much. If you don't have any questions, then we'll switch on to the next presentation.
Maybe I guess it is having losses, right, sir? So like it will be reduced, no, sir, like compared to the before value.
Mm, Actually, you are supposed to link up with the refractive index with permittivity. There is a relationship between refractive index and permittivity. If
Okay,
you
sir.
try to look into that, then you'll come to know why it is a plus or minus. Okay,
Okay, sir.
just have a look on
Thank
that.
you.
And you need to even mention the dependency of the frequency for a given specific material, how the permittivity is getting affected with respect to frequency, and where are the applications. Specifically, because we are dealing with antennas, where the electric material is a part of a microstrip patch antenna. So for different frequencies, how the dielectric material is going to behave, because which type of dielectric material is has to be chosen for designing the antenna. In that particular context, this information is very much required. Anyway, thank you so much for your nice presentation.
Thank you,
Uh,
sir.
yeah, we'll switch on to the next person. Yeah, over to you.
Sure, sir.
Yeah, Sabala Sri Narayan Reddy, over to you. Please go ahead.
Is my screen visible, sir?
Yes, it is visible. Go ahead, please. Make it full screen and start.
Okay, sir. So, hi everyone. My name is Adi. I'm from section B. So, we are going to discuss Friis transmission equation today. So, what does Friis transmission equation signifies? So, it is nothing but if there are two antennas, one is receiver and another is transmitter, how much of the power that is transmitted by the transmitter antenna is going to be um, received by the receiver antenna. So that is going to be calculated by using this formula. So let us suppose the total power that is transmitted by the transmitter is going to be PT. Then power density would be PT by 4 pi r square. If we take an isotropic antenna, if we assume that the antenna is isotropic, then it is going to be divided by 4 pi r square, since it has spherical um, radiation pattern. So, and also we have to again introduce a new term, GT, where GT is transmitting gain. So why should we introduce this term is that if we are taking isotropic antenna into consideration, it is going to radiate the power equally in all directions, right? But in ideal, I mean, it is an ideal case, but in practical case, it is not going to happen. Like the antenna is going to have a directivity. It will radiate more power in one direction and maybe less power in another direction. So it is going to vary, right? So we are going to multiply this power density with GT, where GT is directional gain. So um, if we take an example, I have a MATLAB simulation. So this is isotropic antenna, where power is going to be radiated equally. So here, if the power density is 1.24 into 10 to the power of minus 4, then in a directional antenna where the directional gain is 6, the power density is going to be 7.46 into 10 to the power of minus 4. So like this, we're going to have different power density in this case. So after that, we are going to consider another term called effective aperture area. So if you ask what is this effective aperture area, it is nothing but the effective area that is seen by incoming wave that is transmitted. So to be more clear, we know that our antenna is not a perfect absorber, right? So the waves that are coming towards it, it's not going to absorb all of it. And there are various factors like directionality, impedance, and polarization. So if there is a perfect absorber in the place of the antenna that we have taken as a receiver, then how much area should that perfect absorber should need to be in, so that it will absorb the same amount of power that this particular antenna is absorbing. So that we can call it as effective aperture area. So we have to take that also into the consideration, because even if we are transmitting a particular amount of power in that direction, the amount of power that is going to be absorbed out of it is going to vary according to this effective aperture area, right? So we are taking that term also. So AE is dependent on wavelength and gain. So if we substitute it, I mean, if we multiply that with the power density that we have got before, radiation intensity, then we are going to get PTZT by 4 pi r square into GR lambda square by 4 pi. So this particular formula is called Friis transmission formula. So let me run another MATLAB simulation to show its dependence on frequency and distance. So if we first look at the distance dependence, if we take a constant frequency, let us take 100 Hertz here. And at that constant frequency, if the distance is 100 meters, then the attenuation is very less, minus 20 dB, near to minus 20 dBm. And if the distance is 500 meters, the attenuation is going to increase. So this signifies that if distance increases, then the attenuation is going to be more, and power that is transmitted to that distance will be less. And if we look at the second figure, that is going to show the dependency on frequency. We have already observed that our equation is dependent on lambda square, right? So we also know that C equals to lambda F. So lambda is inversely proportional to frequency. So in turn, this makes our whole equation to be inversely proportional to the square of frequency. So if we take a particular distance, let us suppose we are taking 10 power 1. At that distance, if the frequency is less for 4G, 700 megahertz, at that particular frequency, the attenuation is going to be lesser when compared to higher frequencies at the same distance. So by this, by these simulations, you can like practically see how our received power is going to change with the frequency and distance. So yeah, this completes my presentation on this particular topic.
Yeah, questions, please. Questions, please. Yeah, Adinarayana, I think the last statement which you have told for high frequencies, the power that is received for a fixed distance, it is reducing as
Yes,
compared
sir.
to lower frequencies. I think this might
Yes,
be
sir.
the reason why when we were far away from the mobile tower, our signal will switches to from 4G to 3G, then 2G, if I'm not wrong, right?
Yes, sir.
Because 2G can
Yes, sir. It is.
travel a long distance, and
5G cannot travel.
2G is going to usually have less frequency. Am I right or wrong? 2G is going to have less frequency compared to 4G and 5G.
Yes, sir. It is going to have less frequency.
If that is the case, it will be having a, I mean, more power will be delivered even for long distance. Even when you try to see this 700 megahertz just for 4G, which you are saying, that
Yes, sir.
enables for transmitting more power for long distances because the wavelength is smaller. The
Yes, sir.
received power also will be very high, right?
Yes, sir.
Mm. Yeah, any other questions? Okay, a very nice presentation. Yeah, thank you. If you don't have any questions,
Thank you.
we will end this session. Thank you all.